We're going to talk about displaying and analyzing data in statistics. There are several good ways to display the distribution of a quantitative variable, and quantitative just means numerical. The most basic is a dot plot. So if we're looking at the heights of 50 students, looks like I have somebody that's a little bit over 76.5 inches, somebody that's 74.2 or 74.3 inches. It looks like we have quite a few people that are bunched around 65 to 66 inches. You get a dot for every piece of data that you have. And so the more dots that are in a certain group, then the more people you have uh, in that inch category, so to speak, in this particular situation. You want to make sure you label the axis and scale clearly. So notice that this is labeled with numbers, and we know that it's height in inches. Dot plots are very good for displaying small data sets. However, it's very clear that this is kind of annoying. You probably don't want to do this by hand. There's 50 dots on here. So we probably don't want to spend a whole lot of time doing dot plots for anything that's bigger than 10, 12, 15, maybe even 20 data points. We probably want to go to something else. And so a histogram is something that works out pretty well. Histograms are similar to bar charts, but we do that for quantitative data. So histograms are for quantitative data. And what we want to do is we want the values plotted on the horizontal axis and the frequencies as heights. The bars in a histogram should touch, which indicates that we're not leaving out any possible values. So typically in a bar chart, when you're doing categorical data, you keep them separate. So eye color, red, yellow, green. Um, I don't know if many people have red eyes, but if you are doing, or yellow eyes for that matter, but if you're doing eye color, you would want to keep them separated, indicating that it doesn't really matter which order you put them in. Whereas with a histogram, you want them in the order that makes sense numerically. Since data is quantitative, there are no natural categories to place it, so we have to define our own, and we call them bins. There's no perfect way to create bins, but we should always have them be the same length so that we don't get confused with how long they are. We don't want them to have any overlap, and we want minimal gaps if possible. Sometimes we're going to have some gaps, but we want to try and eliminate gaps if possible. Ideally, it's nice to have between 4 and 10 bins, and we want them to start and end at nice values. So what bins could we use with this data? Well, if I'm looking at this data, I could do a variety of different things, and however I do it, it's going to make my data look slightly different. So let's say I go up by twos. So 58 to 60, 60 to 62, 62 to 64, and so on. Basically, what I do is I'm going to count how many observations are in each. So there's 1 between 56 and 58. There's 3 between 58 and 60. There's 9 in between 60 and 62. There's 6 in between 62 and 64. Anything that's on a line, we move over. And it looks like this one is actually on the line. So I'm going to move that into the 64 to 66 category. So basically anything that's on a line, we kind of round up. And so what I would do is I would say 56, 58, 60. So I have 11 things here. And then what I want to make sure that I do is I accurately represent how high they are. So I want to go up by an even amount of things. So I want to try and keep my spaces as good as possible. And I need to go up to 13 because that's my highest one. And so I have 1 from 56 to 58. I have 3 from 58 to 60. I have 9. And drawing on the smartboard is not that easy. So that's a histogram. I could also have changed my bins. So let's say I made bin sizes of 4. Or I could have done bins starting at 57 and then I would have had 10 bins of size 2, maybe. So if I started at 57, I could have had 10 bins of size 2. If I start at 56 again, maybe I can do bins of size 4. So this one has 4 in it, this one has 15 in it, this one has 20 in it, this one has 9, this one has 1, and then unfortunately I would have to go all the way to 80 in order to make sure that my bins keep the same size, and then that one would have 1 in it. So I can also do another histogram that kind of uh, looks a little different. Um, it's going to look different, but it's going to represent the same data. And so that's something that's kind of important. When you make a histogram, make sure you label the scales and axes. You should always start at 0 on the vertical axis. You should not start at like 10 or 12. The bars in a histogram should touch, like we just showed. So that's kind of important. Relative frequency histogram looks exactly the same as a regular histogram. Instead of these being numbers on the side, so this was 1, this was 2, and so on, all the way up to 13, instead of them being numbers on the side, they can be percentages. So we had 50 people. Since we had 50 people, one person is 0.02, or 2% of the total population. So our histogram will look exactly the same. This is going to end up going all the way up to 0.26. So what we're saying is about 1/4 of our observations were between 64 and 66 inches. Just another reminder, you might want to put heights in inches on the bottom because you should label things. But I kind of forgot, so I hope you don't forget on the quiz or the test. Note, a common mistake is to make a histogram by using one bar for each observation, where the height of the bar represents the value of the variable. And that's a common mistake, but it's so hard for me to even visualize because I've been doing them correctly for so long that I don't even know what it looks like. So I'm not going to show you so that you don't mess it up. There are methods for creating histograms with unequal classes, so like different bin sizes, but we're not going to do that. If a frequency distribution has non-bounded classes like 12 or more, you can't make a histogram. So if it's something like how many um, how many referrals have you had in your high school career? 1 to 3, 4 to 6, 7 to 9, 10 to 12, more than 12. You can't make a histogram with something like that. A stem and leaf plot is another way to display relatively small numerical data sets. You have the stem on the left in this part and the leaf on the right. So the stem is the first part and the leaf is the last part. So for example, these freshman male weights, 97 represents 97. 102, we would have 10 and then a 2. So this represents 102 for the weight. Notice we have a key at the bottom. That's kind of important. And so they listed them all. You want to put them in order. They're called Stemplots also. And if you tilt your head to the right, it kind of looks like a histogram. So that's something to keep in mind. This basically is kind of like a histogram, except it ends up it keeps the numerical data. Okay, so numbers to the left are the stems, to the right are the leaves. You must include a key. You wanted to label in a title, and leaves should be single digits. So for example, 130, 132, and 139, these numbers over here have to be single digits or else it's very confusing. So all leaves have to be single digits. It's best if the leaves are in numerical order, but it's not required, and stem plots look very similar to a dot plot or a histogram tilted to the side, with the stem plot preserving the data. Back-to-back stem plots are very useful for comparing distributions. So the freshman male weights and put them back to back with female weights. And so then we can kind of see what's happening. So freshman weights, I have males on the right and I have females on the left. So 93 and 99, 100, 104, 109, 111, 113, 113. Notice what happens if I have two of the same number. I just put both of them on there. 121, 125, 126, 128, 142, 159, 185. So if I wanted to compare these, um, it's pretty easy to do that now that I have seen what the data looks like. Um, Now that I've done that, I have to get that out of the way so we can learn more stuff. But basically, I have freshman male weights on the right and female weights on the left. If I notice, the male weights have much more variability, they're spread out, and their mean looks bigger. So it looks like males tend to weigh more than females. Not in every case, obviously, but females are much more clustered down um, in the lower weights. So if you need that, rewind. When the data set is very compact, it's often useful to split the stems. We call this a split stem plot. So, body temperatures. Let's take a look at what we would typically do in this. Um, if I have body temperatures, I might make a key for an original stem plot, and 96/3 would be 96.3 degrees Fahrenheit. So this seems to make sense. Um, I have body temperatures. Then I go. So if I look at this, pretty straightforward. There are lots in the 98s, pretty grouped around that, and we should be pretty good to go. Um, but I think we're missing something if that's how we draw this stem plot. So I can do the same thing. I can say body temperature, and my key can be exactly the same. So I'll move that over here. But if I split the stem plot, 96 low, 96 high, 97 low, 97 high, 98 low, 98 high, 99 low, 99 high. Now, why might we want to do this? Well, there are a ton of data points in the 98s, and it may be good to see, just how spread out these things are because 98.1 and 98.8 are pretty different when it comes to body temperature. So because the data is really compact, we may want to space it out and see things a little bit better. So 96.3, by the way, I'll count low as anything where the decimal place is between 0 and 4, and high anything where the decimal place is between 5 and 9. So I'll keep 5 of these tens digits in, or tenths digits in each category. 96.3, 97.6, 97.8, 97.9, 90. Oh, wait, those are high. So I didn't even put them in the right spot. What becomes much more obvious when we space this out is that there are still a lot of 98.5 through 8, and that this person's in big trouble. Uh, when we look at this, they're very cold. There's nobody else but that's within 1.3 degrees of them, and pretty much everybody else is within 2 degrees of each other. So, because that's the case, we would be very concerned about this person that has a 96.3 degree temperature. That's one of the benefits of the split stem plot in a situation like this. When the data is often spread out, we may want to truncate the data. For example, if we are doing grocery shopping, we probably don't care that much about the decimal places because we would have to go 10, 11, 12, 13, 14, 15, 16, blah, 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 all the way down to 52 if we were going to just care about the dollars. And then we would still have to get rid of the pennies, basically. So it's probably better to just do something like this. This means $10, and we're just ignoring all of the decimal places after that for our bill. So our grocery bill is going to look something like this. So $10, $13, $15, $18, $20, $20, $27, $32, $37, and $52. This still gives us plenty of information. This was a very high grocery bill for us. We still see the gap in the plot, and we don't really need to worry too much about the cents in this case.